Now let's talk a little bit about design resolution, and I will explain what I mean in the previous case by saying that you have two effects, two interaction effects instead of just one. Okay, so let's start with the following. Let's say you have 4 factors. So it means that in this, if you run full factorial design, so you have 16 runs and 16 trials, you will be able to calculate 16 different things, 16 different effects. First of all, it's an average. Okay, it's an average effect. Then you can calculate 4 main effects, 6 2-factor interactions, 4 3-factor interactions, and 1 4-factor interaction, right? And you remember we use these 5 as a source of noise, because we know that all interactions with more than 3 factors or more, it's a noisy. Okay. Now look, what can we estimate with half fractions? So if we use 2 in the power of 4 minus 1, so we use 8 instead of 16 runs. You remember that if you use half fraction, we need to confound at least one main factor with the interaction factor, right? With the interaction effect. Okay. What is confounding pattern for full factorial design? So if we use full factorial design, we don't have any confoundings at all. How you can see that? You can see that if you multiply any 2 effects. For example, if you multiply the values for A and B, or you multiply the values between A and ABC, or multiply the values between A and AB, you will find out you will never get this identity vector. So it means that all these factors, all these vectors, they do not covary. The correlation between these factors is 0. So it means that you can resolve every single effect from main factors and from all interactions. Every single effect is resolved. Okay, so there are no confoundings at all. Okay. Now, if you look at our example with modification of bearing, how many confoundings you have? You remember that that's the design generator we used, and this is the identity equation, right? So what it means? It means a very simple thing. You remember that, for example, A times A is I. So you can say that A is confounded with A. That's reasonable, right? You change A the same way as you change A. Okay. Now think, what if you multiply A and B, for example? Look, if you multiply A and B, we will have, I will just multiply it here. We have plus here, we have minus here, minus, then we have plus, then we have plus, minus, minus, and plus. So this is a vector for the A and B, right? So you can see it here as well. Okay. But now look, what if you multiply C and D now? So this is C, and this is D, right? Again, I will write it here on the side. So look, this is minus, you have plus, then you have minus, minus, then you have plus, plus, then you have minus, minus, and plus. So what it means? It means that the A and B interaction between A and B have the same pattern as an interaction between C and D, okay? Absolutely the same, identical. They correlate fully. So it means that if we see an effect from interaction between A and B, it can be an effect from interaction of C and D. So it means that these 2 effects are confounded. 2 effects are confounded. How we can see that? Well, again, that's what we can calculate from this one. Okay. Okay. So you have I is A, B, C, D, right? So it means that A will be confounded with B, C, D. B will be confounded with A, C, D. For example, D will be confounded with A, B, D. That's not a problem. So you can see that all main effects are confounded with 3-factor interactions, and 3-factor interaction is noise. So when we confound something with noise, we still can see the main effect, right? But if we come to the 2-factor interactions, you can see AB is confounded with CD, like we just shown you before. Then AC will be confounded with BD, and then AD is confounded with BC. So it means that in this, for example, in this case, if we see an effect, it can be an effect from this interaction, it can be an effect from this interaction. We cannot resolve this effect. Okay, so this is the confoundings, and this is the price we pay for having less trials and use less time and money for the experiments. Okay, so in this case, we don't see the clearly 2-factor interactions. They are confounded, but we still can see the main effects. We can see still which factors are the most important. Okay, so in this case, for example, if we say C, it will be confounded with A. This is an error, of course. This is C. C is confounded with ABD, and D will be confounded with ABC. Okay, with ABC. So all main factors are resolved because they're confounded with three-factor interactions, which is nice. So we will be able to see the effect from main factors, but we will not be able to see the effect from two-factor interactions clearly because they are confounded with each other. Okay, so that's the idea. That's the idea. And now if we get back, so this is the full confounding patterns. You can see it here. So main effects are confounded with three-factor interactions. Two-factor interactions are confounded with each other. So you can say that one-factor interactions is confounded with three-factor interactions. Two-factor interactions is confounded with two-factor interactions. Okay. And then there is a special characteristic of any fractional factorial design which takes into account these confounding patterns, which is called resolution. So in this case, we have a design of resolution 4. You can think of resolution very easily. If resolution 4, it means that 1 is confounded with resolution minus 1, right? So in this case, if resolution is 4, it's 4 minus 1 is 3, right? 2 is confounded with resolution minus 2 and so on. So this is the resolution. So resolution 4, it means that main effects will be confounded with three-factor interactions, and then two-factor interactions will be confounded with each other. Okay. So design resolution characterizes the confounding pattern. Okay. So if design of resolution R, it means that there is no p-factor effect confounded with another effect containing less than R minus p factors. Okay, so this is the official definition of the resolution. And then the smallest meaningful resolution is a resolution of 3. In this case, for example, it can be a design 2 in 3 minus 1 with this generator. So in this case, you can easily see that all main effects will be confounded with two-factor interactions, right? All main effects will be confounded with two-factor interactions. So of course, it's still okay because the two-factor interactions, the magnitude of these interactions is smaller than the magnitude of main effects, but still you will have this confounding pattern. Okay. Then if resolution is 4, it means that you have one-factor interactions confounded with 3, two-factor interactions confounded with 2. Okay. So in this case, if we use this relation, this generating relation, of course you can use some others, and then the resolution will be even smaller. Okay. Then you can also think that the resolution 5 and 6 are even better. The higher resolution, the better. I would recommend to very rarely use resolution 3 because it's only for looking at clear main effects. Okay. But then resolution 4 is sort of a gold middle. Then resolution 5 allows you also to see an effect from two-factor interactions clearly. Okay. So now if we get back to our example, you can see that indeed we have because we use this relation, you remember D is ABC. So if we multiply both sides to D, we will have DD equal to ABCD. And then you know that this is identity. So this is the vector with pluses only. So this is our generating relation, ABCD. And then from this relation, we know that all main factors are confounded with three-factor interactions, and then two-factor interactions are confounded with each other. So that's why we have this notation for the interaction effect. So all two-factor interactions are confounded with each other.